Welcome to the deep dive. You know, it's pretty amazing when you think about it. How does the complex stuff we write, like in Python or C++O, actually turn into raw electrical signals inside a chip?
It really is. It's like translating a novel into just flicks of a light switch, but billions of times a second.
Exactly. So today, using the great sources you've provided, we're diving deep into that whole journey. We want to trace how an idea becomes, well, those perfectly timed flickers, the whole instruction life cycle.
That's the mission. And it sounds incredibly complex, but the core idea is surprisingly straightforward, even if the speed is mind-boggling. The absolute baseline. A computer only understands one thing: binary. Zeros and ones.
Just zeros and ones, nothing else.
That's the processor's native language.
Okay, but nobody actually writes raw binary, right? I mean, maybe some hardcore engineers back in the day, but...
No, not anymore. It would be impossible. That's why we have what you could call the abstraction ladder. It helps us humans bridge that huge gap.
All right, we start with high-level languages. Python, Java, C++, Turf. Stuff that feels, well, almost like human language sometimes.
Almost, yeah. They let us express ideas. But even going down a step to assembly language, that's already much closer to the hardware.
Assembly, right. With those little codes, the mnemonics.
Yeah.
Like MOV for move or ADD for add.
Exactly. Mnemonics, they stand in for the binary sequences, make it a bit more readable. But, and this is key, everything eventually has to become binary.
Everything, no exceptions.
No exceptions. Whether it's compiled beforehand or interpreted on the fly, it must be translated into those zeros and ones before the processor can actually do anything with it.
Okay. So it gets translated down to binary. What's the basic unit the processor works with then?
That's the machine instruction. Think of it as the smallest possible verb the computer understands. Adding numbers, moving data, jumping to a different part of the program. Each one is a specific machine instruction.
A tiny command, basically.
A tiny binary command.
But how does the processor know what a string of zeros and ones means? Like, this sequence means add, but this sequence means store. There has to be some kind of structure, right?
Absolutely. It's not just random bits. Each machine instruction has a defined structure. Typically, it's broken into two main parts.
Okay, what are they?
First, there's the operation code. That's the verb. It says what to do: add, subtract, compare, load, store.
Got it. The action.
Right. And second, you have the operands. These are the nouns. They tell the processor what data or memory locations to perform that action on.
So add is the opcode, and maybe register 5 and register 6 are the operands.
Precisely. Add the contents of register 5 to register 6. That structure opcode plus operands lets the processor quickly figure out what needs doing and with what data. It's very efficient.
Okay, that makes sense. So we have this structured binary instruction. But something needs to manage the whole process, right? Tell all the different parts of the chip when to act.
Exactly. That's the job of the control unit. It really is like the conductor of an orchestra, just like the sources say.
The conductor. Okay. So what's it actually doing?
It takes that decoded instruction and sends out perfectly timed electrical control signals to all the other components involved.
Like
the memory to fetch data, the registers to hold temporary values, and crucially, the arithmetic logic unit, or ALU.
The ALU. That's where the math happens.
That's where the math and logic operations, the adding, subtracting, comparing, actually get performed. The control unit makes sure the data arrives at the ALU at the right moment, tells the ALU what operation to do based on the opcode, and directs where the result goes. It synchronizes everything.
Synchronization seems key here. But how does it keep everything perfectly in sync? What provides the beat for the conductor?
That's the clock, the system clock. It's the heartbeat of the processor.
A heartbeat. I like that.
And it beats fast. Modern processors have clocks generating billions of pulses, electrical highs and lows every single second. Billions!
Billions per second. It's hard to even picture that. So what does one pulse actually do?
Each pulse acts like a timing signal. It allows one tiny step, one micro operation to happen. Think of it as the smallest possible action the hardware can take, like moving a value between two registers or enabling the ALU to perform its calculation.
Okay, so one clock tick, one micro operation.
Exactly. And there's something called the sequencer, often part of the control unit, that uses these clock pulses to step through all the micro-operations needed to complete a full machine instruction. Fetching might take a few pulses, decoding a few more, executing might take several, storing another few. The clock ensures these happen in the right order and don't interfere with each other.
Wow. Okay, so we have the binary instruction with its opcode and operands. We have the control unit conducting everything. And we have the clock providing this incredibly fast beat, driving the micro-operations. Let's put it all together. What's the exact cycle every single instruction goes through?
Right. This is the fundamental instruction cycle. It's usually described in 4 main steps: fetch, decode, execute, and store.
Fetch, decode, execute, store.
Yeah.
Okay. And this cycle just repeats over and over.
Constantly. Millions, even billions of times per second in total, depending on the processor and what it's doing.
Let's walk through it. Step 1 is fetch.
Fetch. The processor needs to get the next instruction from memory. Its address is usually held in a special register called the program counter.
And fetching from memory.
Yeah.
That can be slow sometimes, right?
It can be the slowest part, relatively speaking.
Yeah.
That's why processors have cache's small, super fast memory right on the chip. If the instruction is in the cache, fetching is lightning fast. If it has to go out to the main system RAM, well, that takes much longer. It's called a cache miss.
Okay, so let's assume we fetch the instruction, that binary sequence. Now what?
Step 2, decode. The control unit takes that binary instruction and figures out what it means. It identifies the opcode, this is an ADD instruction, and identifies the operands. Okay, I need the data from these 2 registers.
It translates the binary into an actual operation.
Precisely. It determines what circuitry needs to be activated to carry out the instruction.
Which leads us to step 3, execute. This is the main event.
This is where the action happens. The control unit sends the signals, the data is moved to the ALU if necessary, and the ALU performs the operation specified by the opcode. If it's an ADD instruction, the numbers are added. If it's a compare, the comparison is made.
And after the calculation or whatever the action was,
Step 4, store. The result of the execution needs to be saved. Usually it's written back to a register on the processor for quick access later. Sometimes it might be written back to main memory.
and
Then the cycle immediately begins again for the next instruction. The program counter is updated to point to the next instruction's address, and it's fetch, decode, execute, store all over again, relentlessly.
fetch, decode, execute, store, repeating millions of times a second. But you mentioned earlier, modern processors are even faster. If this 4-step cycle is the fundamental process, how did engineers squeeze out more speed? You can't just make the clock infinitely fast, can you?
Right, there are physical limits to clock speed. Heat, signal propagation delays. So engineers got clever. The big breakthrough was, and still is, pipelining.
Pipelining. Okay, what's the idea there?
Think of the 4-step cycle, like one person building a car completely, from start to finish. Fetch the parts, assemble the chassis, install the engine, paint it. Only when that car is done can they start the next one. It works, but it's slow.
Okay.
Pipelining turns it into an assembly line. You have different stations. While one car is being painted, the next car is having its engine installed, execute. The car after that is being assembled, decode. And the parts for the car after that are being fetched.
I see. So you overlap the stages. You don't wait for the first instruction to finish completely before starting the next one.
Exactly. That's the core idea. While instruction 1 is in the execute stage, instruction 2 can be in the decode stage, and instruction 3 can be in the fetch stage, all happening at the same time using different parts of the processor hardware.
So multiple instructions are kind of in flight simultaneously?
Precisely. It doesn't make any single instruction finish faster, but it dramatically increases the throughput, the number of instructions finished per second. You're keeping all parts of the assembly line, all parts of the processor busy more often.
That sounds way more efficient.
Okay.
Doesn't that get incredibly complicated? What if, say, instruction 2 needs the result from instruction 1, but instruction 1 hasn't finished executing yet?
You've hit on the main challenge of pipelining. Those situations are called hazards or dependencies. If instruction 2 needs data that instruction 1 hasn't produced yet, the pipeline has to stall.
Stall, like just stop.
Yeah, instruction 2 just has to wait in its stage until instruction 1 completes enough for the data to be ready. Stalls waste time and reduce the benefit of pipelining. So processors have complex techniques like data forwarding to try and get the result from instruction 1 directly to instruction 2 as quickly as possible, sometimes bypassing the normal store step.
Wow. Okay, that's already complex. But the sources also mention something even trickier. What about if statements, conditional branches?
Right. Branches are another major headache for pipelines. Think about it. The processor is fetching instructions way ahead of time. If it hits an if condition, it doesn't know yet whether the condition will be true or false. Which path should it start fetching instructions from?
It has to guess.
It has to guess. This is called branch prediction. Modern CPUs have sophisticated prediction units that try to predict, based on past behavior or patterns, which way the branch will go.
And if it guesses right.
If it guesses right, fantastic. The pipeline stays full, instructions keep flowing, and we maintain high speed. Processors are actually very good at this, often predicting correctly over 90% of the time.
But what if it guesses wrong?
A misprediction. That's costly. If the processor guessed wrong, all the instructions it speculatively fetched and started executing down the wrong path have to be thrown out. The entire pipeline gets flushed.
Completely emptied.
Emptied of all the incorrect work. Then the processor has to start over, fetching instructions from the correct path determined by the actual outcome of the condition. This flush and restart process wastes a significant number of clock cycles and really hurts performance. It's a high-stakes guessing game driven purely by the need for speed.
So we went from simple binary instructions all the way to the processor, literally trying to predict the future to keep things moving fast. What a journey.
It really is. It shows how every single layer matters. The high-level language lets us think, the compiler translates, the binary instruction provides the structure, the control unit directs, the clock sets the pace, and techniques like pipelining and branch prediction push the speed limits. It all has to work together.
Yeah, it's this incredible symphony of hardware and software working in lockstep.
That's a good way to put it. And ultimately, like the sources conclude, this whole intricate dance is what transforms our abstract human ideas into concrete digital reality millions and billions of times every second.
So for you, listening to this, the real takeaway might be just how tightly coordinated this whole thing is. Think about that pipeline, juggling multiple instructions while the clock is ticking in billionths of a second.
Right. And maybe a final thought to chew on. Given how critical that perfect split-second timing is, especially with pipelining trying to overlap everything and branch prediction guessing ahead, what does that tell us about the physical limits?
Physical limits.
Yeah, if making a wire just a tiny bit longer on the chip introduces too much delay because the signal can't get there in time for the next clock pulse, if everything relies on signals arriving at exactly the right nanosecond, what does that intense need for synchronization imply for how much faster or even how much smaller we can realistically make these chips in the future? Are we heading fundamental walls imposed by the speed of light itself within the silicon?
Wow. That's definitely something to think about. The sheer speed becoming its own bottleneck.